our next speaker. I've had the pleasure of actually seeing this man talk before at GopherCon India, GopherCon Dubai, going to the world's tallest building with him. His fun fact is he was a nationally ranked wrestler in high school. And I'm going to totally butcher his name right now. Aditya Mukerjee.
Great. So great to see so many people here today excited to be talking about Go. My name's Aditya. I am a risk and systems engineer at Stripe. If you're interested in talking about how payments work or how we combat fraud from the dark web or how to make your systems more observable, come talk to me. But today, I'm here to talk about a project called Gitgo. How many of you use Git regularly? Okay. Not surprising for a Go conference. How many of you called yourself Git experts? OK. So Gitgo is a pure Go, open source, clean room implementation of Git. And there are a number of reasons that we decided to write Gitgo. Primarily, we can perform Git operations from Go source code, but we also get the additional portability and simplicity that comes with Go code over C. But most importantly, why not? Why not rewrite Git in Go? Rewriting Git in Go gives us a tremendous opportunity to transcend some of the limitations of C and to rethink the design of the software, and therefore to rethink what we can actually use Git to do. So I'll share with you a little secret. Not everyone knows this, but Git wasn't actually intended to be a version control system. It was originally intended to be a file system for people to build a version control system on top of. And then it turns out that Git itself made a pretty good version control system, and so people just kept using that. But it's right there in the man page. Git is the stupid content tracker. It's not the stupid source control tracker or the stupid software tracker. It's a stupid content tracker. So when we talk about performing Git operations from Go code, I don't just mean interacting with source code, though that's definitely a big part of it. I'm also, in other words, you can think of Gitgo as a pure Go library for interacting with a decentralized userland file system that can preserve historical state and synchronize data. So these are some of the things that Gitgo enables us to do in Go. We can use the Git file system for backup and content management. If we have a lot of files and we want to manage which hard drives they're on or which boxes they're on in a cluster, we can use Git to keep track of them. We can use Git for distributed build systems or for establishing lightweight consensus. We can synchronize intermediate build states and use Git's binary diffing to get performance out of that. And some of these applications that I'm talking about are already in use using Gitgo. So this talk could just as easily have been titled Writing a File System in Go or Writing a Distributed Build System in Go. So if any of these applications sound interesting to you and you like working on open source Go projects, come take a look at Gitgo. Git and Go may be the two most important pieces of software for every Go programmer, and Gitgo is a great way to really get to know their ins and outs. Today, I'm going to talk about 5 discoveries that we made when writing Gitgo, which are relevant to all Go projects. And they all relate to the way that interfaces work in Go, both interface types and also interfaces as a software pattern. So just so that we're all on the same page, a little bit about how Git works. Have you ever seen a friend's computer that looked like this? Yeah, I thought so. It sounds silly, but that's almost exactly what Git does. If you use Git, you'll know that commits are referenced by their SHA hash, which looks something like this. Git really only knows one entity, and that's the Git object. And the object comes in 3 main flavors. Commits are one of them. But the actual information that's contained in a commit, like the commit message, is stored in the .git/objects directory. And it's zlib compressed, but if we decompress it, the contents are human readable. So as you can see, it tells us the parent commit, it tells us the author, it tells us the commit message. But the first line gives us the SHA of a different object altogether, which is a tree. And that refers to a single snapshot of your directory tree. And that tree object is also stored in the .git/objects directory. So if we look up the object that has that name, 4659AEC, we can read that file and get a list of blob objects and their file names. So we get the names of the objects right there, and then we get the names of the file names. So let's try reading one of those blob objects. You can see here that when we decompress a blob object file, we get the full contents of that original file again. And that's because whenever you do a git commit, Git takes a snapshot of every single file in your directory, exactly what we saw a few moments ago with all those dated folders. So notice that this blob object doesn't actually contain the file name, and that's by design. If a file doesn't change between two commits, both snapshots can still share the same blob object. Git deduplicates that. So to summarize, Git objects can be commit objects, tree objects, or blob objects. Commits and trees can both point to other objects, and it's recursion all the way down until you get to all of your blob objects. And this is important because a lot of people think that Git stores diffs, and that's actually not true. Whenever you do a git diff or a git log, all of those diffs are generated on the fly. And that's why checking out a branch in Git is so fast. Git isn't reconstructing all of your files from the entire version history. It's whenever you check out a branch, it just needs to see which blob objects are contained in that commit, and then copy those blob objects to your directory. So re-implementing all of this part in Go is easy. Go already supports zlib decompression, and as we saw, the uncompressed object files are all human readable, and they're straightforward to parse. So our first discovery about Go might not be much of a surprise. Layered interfaces are more flexible than union types, and they give us better type safety. As you saw, Git already stores everything as objects, but there are different kinds of objects. And in C, we handle this using union types. But since we're using Go, we can do better than that. In Go, we have interfaces. And if we layer our interface types in Go, we can get all of that same flexibility of union types and more, but with additional type safety. Interfaces mean that we can parse objects not based on what they are, but based on how they behave. And layering that interfaces means that we don't have to ask for that behavior all up front at once. We can do it in stages. And this is similar to how the I/O interfaces work in the standard library. The standard library, you have readers, you have writers, you have seekers, and some types will satisfy all three of those interfaces, like the file type. But some types just satisfy one or two of those. So the way that we have this here, the Git object is itself an interface. And tree is also another interface which combines two interfaces. It combines the Git object interface with the tree-like interface. And the reason we do that is because there are actually a few different things that can behave as trees. We're not going to get into that, but having these layered interfaces means that we can support multiple implementations of them. So at first, we started implementing object parsing by bootstrapping Gitgo, by using the actual Git objects in the repository for our project in our tests. And I mean, this sounds like a reasonable idea, right? As long as you don't rebase or force push, your Git history is going to be immutable, right? That's wrong. The history that Git represents is immutable, but the way that it represents that history may actually change. If you have a SHA that represents an object, like a commit or a blob, you can always count on that object being stored somewhere in your .git directory, but it might not always be stored in the same place or in the same way. Specifically, Git has a custom-built compression algorithm for handling binary diffs. And now you might be thinking, well, didn't he just say a moment ago that Git doesn't store diffs? That's true. Git doesn't store anything that resembles the diffs that you ever interact with when you use Git. But it does have a way of compacting objects to reduce redundant information stored. We saw the first way that Git does this using hashes. It can deduplicate blob objects that are 100% identical. But if even a single byte is different, like in this example, just that one exclamation mark, they're going to hash to two completely different things. So that means that if we're making a lot of small changes to the same files over and over again, we're going to be storing a lot of duplicate data. And think about that for a second. For a version control system or a file system for version control, that's a bad property to have because it's all about making lots of small changes to the same files over and over again. So to fix that problem, whenever you push or pull a branch, Git will garbage collect the duplicate chunks within objects by storing them in a special object that's called a pack file. And a pack file is a double-layered compression scheme that stores binary diffs. And again, this has nothing to do with the diffs that you interact with. These are binary diffs, and they're dynamically generated and regenerated whenever you push and pull branches. And the goal there is actually to reduce network usage. It's to make Git clone faster. Now, I could talk for quite a few hours about pack files. If anyone's interested in the really, really gory details, come talk to me afterwards. I'll talk your ear off about them. You can also check out an article I wrote unpacking Git pack files, which gets into the really nitty-gritty about it. But I just want to give a little taste of what's involved, because it'll bring us to the second discovery that we made about interface types in Go. Let's say that we had these 3 strings and we want to store them. Well, we'd store the first one, and for the second, we'd say it's basically the first string, but just with an exclamation mark. OK. But for the third, you can see that it's not just so simple as concatenating one of the other 2 strings with something else, but there is some redundant information there. There is some way to squeeze some bits out of that. And so here's where Git would use a custom-built algorithm for determining the shortest function that relates the first 2 strings to that third string. And of course, unlike the simple example, the real packfile algorithm is context agnostic. It doesn't actually care that the files are text, or they could really be anything. And so once you do that, we just take each component and zlib compress it individually, and then concatenate all of those into a pack file. And there you go. You've made a pack file. But pack files gave us an important discovery about Go, which is that we have to pay attention to the contracts of the interfaces that you're using. In fact, there's a small gotcha that's hidden in the reader interface. So the zlib format is prefix synchronized. That means that you can append arbitrary data to the end of a zlib file without changing how it's decompressed. And that's not a Go property. That's a property of zlib itself. The decompression step will just keep reading until it's able to reconstruct the entire file or the object, and then just ignores everything after that. And so that arbitrary data at the end, that could be anything. It could be another zlib object. As we saw, that's what Git does. It stacks many zlib objects into a single pack file. So if we want to parse pack files in Go, you'd think, well, we just initialize a zlib reader at the very beginning, keep reading until we actually get something, and then we now have our first object, and then we know where that first reader left off. We can initialize a new zlib reader and keep reading to get the second one. And it would be it's like a linked list of zlib objects. It's very Lisp-like. I used to be a Lisp programmer, so I like this idea. But unfortunately, Go's zlib reader is non-exact. That means that it might actually read more data than it needs. So once you've read that first object, you don't actually know where to start reading the next, because it might have actually started to read the first few bytes of the next object and not told you about it. And there's actually no way of knowing how much data it really used from your original buffer. And you might be thinking, well, no, doesn't the read method give us the number of bytes from the reader? And the answer is no. It gives us the number of bytes written into the slice that you provide. And for many readers, those 2 things are going to be the same thing. But if you're talking about compression, hopefully the number of bytes that you read from your compressed version is going to be different from the number of bytes that you're reading in your uncompressed version. If not, you don't have a very good compression algorithm. And so read will return the number of uncompressed bytes. And that's not what we need. What we need is the number of compressed bytes that were read from the original file. And unfortunately, to make matters worse, the zlib reader does its own internal buffering. So even if you wrap the file in your own buffer, you can't know where that so-called junk data really began, because it might still have pulled some of that into its internal buffer. And it turns out that parsing Git pack files is actually a lot harder than it otherwise would be if we had this information. Since we don't have access to it, we need to read this other, even more complicated format that's essentially an index file. It tells you where what the byte index are, where everything begins. And so to be fair to Go, Go isn't alone in this. The C libraries that are usually used for zlib compression and decompression are non-exact. Rust also does the same thing. In fact, there's only one language that I'm aware of that has an exact zlib implementation if you want to use one, and that is Haskell. So go Haskell, I guess. But now, don't get me wrong. Like Go's IO interfaces are amazing. I absolutely love them. I've been writing Go for going on 5 years now, and this is the only real frustration that I've had with them. So that's quite impressive for an interface design. But it's an interesting corner case that we ran into, and it's an important lesson to learn about interfaces in Go. They're a powerful abstraction, but sometimes there's an impedance mismatch between what you want to do and what the interface will let you do. Sometimes you can work around that as we do here, but sometimes it means that you can't actually use the interfaces that you want to use at all. Now, our third discovery about Go involves concurrency. And it's a great tool for defining state machines as an abstraction. If we git check out a branch, there are a lot of independent steps that need to happen. And some of those will depend very tightly on each other, but some are completely unrelated, and they only really need to come together in the final step. So even without parallelism, even if we do everything in serial, concurrency is a powerful tool. Because concurrency it's not about executing things in parallel, it's about decomposing your logic into independent components and defining the interfaces and invariants that relate them. So as an exercise, sit down and draw out your call tree for your program. You'll end up with something like this. So function f will dispatch to f1, f2, or f3, and it uses maybe an if statement or a switch statement to decide which functions to call. And they'll do their own thing, but at some point they'll all come together and they'll still call, G will end up getting called. And then G will also do some dispatching, and maybe it does that on polymorphism and interface types instead of using explicit branching. But you'll end up with something that looks like this. You'll end up with some nodes that end up having a lot more inbound or outbound edges than others. And those states that have the inbound and outbound edges are oftentimes places that you'll want to use a channel to communicate. And when you do that, every group of nodes between two channels becomes its own Go routine. So concurrency lets us construct state machines that have very narrow responsibilities, like reading an index file or extracting an object from a pack file. And when we use this approach, we can think of channels as invariants or contracts within our program. A function can say, well, I don't know whether the object that I just received on this channel came from a pack file or a raw object file, but I do know that it's a valid Git object. And even if this all happens in serial, we get the benefit of simpler code and more testable code. If you really want to take this to the next level, you can try enforcing that your channels never actually contain concrete types, that they only ever contain interface types. If you do that, the implicit dependencies and the coupling that you have without realizing it will become very explicit very quickly in your call tree. So our fourth discovery is about the error interface. Now, Git itself uses C-style error handling, which is returning an integer status code. And that's functionally the same as doing if error is equal to or not equal to nil. So we could do the same thing for Gitgo. But since we're not using C, why not take advantage of the more advanced error handling that Go gives us? We can return arbitrary information along with our error, which lets us decouple our code even more. So for example, we might encounter an error when extracting an object from a pack file. Like maybe we're reading a repository over a network, which is actually something that Git written in C doesn't let you do. If you want to read a repository over a network, we might encounter an error and if our connection drops. And we could retry that with a delay, but sticking that logic into the pack file function is kind of awkward. The pack file parsing really shouldn't need to know anything about network communication. Git fetch already does, but we need a way for git fetch to be aware of that without the pack file function having to know that it exists. And so instead of forcing tight coupling between all three of these functions, we can just ask the interfaces, ask the errors how they behave. We can use a local interface type here to see if an error happens to give us the ability to replay it. And if so, we can do that within the git fetch function. And the interesting thing about this is the HTTP dir knows what concrete type of error it's returning, but the pack file function doesn't know anything about replaying still. And git fetch still doesn't even know the real identity of the error. All it knows is how it acts. We've completely separated and distilled our functions into the independent components that we need, the true essence that each function actually needs to be aware of, and absolutely nothing more than that. Our final discovery about interfaces is that if you design your interfaces well, you will get great performance out of them. Now, a lot of people are hesitant to use interfaces sometimes because they think that they're going to take a performance hit when they use interfaces instead of concrete types in their code. And it's true that, yes, there is some overhead that you introduce when you use interfaces instead of concrete types. But in reality, if you design your interfaces well, if you think about them and if you're mindful of how you use them, you're actually going to get far more performance out of them. We made absolutely zero effort up front into optimizing Gitgo for performance when we first wrote it, and yet these are the very first benchmarks that we ran. We could already load and parse 100 Git objects every millisecond. And I'd like to take full credit for this, and actually I will take some credit for this. But in reality, a lot of this, most of this just comes from the fact that we were piggybacking off of the existing interfaces defined from the standard library, the I/O readers and writers, and the crypto libraries that leverage them. If you are mindful of how you stack your interfaces, of what parts of code that you are chaining together, and what abstractions you do and do not need to expose, interfaces aren't a way to increase your overhead, reduce your performance. They're a way to strip out the parts that you don't actually need. And that's how you get good performance in Go code. So these are the 5 discoveries that we made about how interfaces work in Go while writing Gitgo. And they're applicable whether you're building a file system in Go, or whether you're writing a distributed build system in Go, whether you're managing source control or source code from Go, or if you're doing something else altogether. But if you are interested in doing any of those things, come take a look at Gitgo. It's open source and it's on GitHub. And it enables us to take full advantage of the file system that Git has popularized for us and achieve the true potential of absolutely everything that Git enables us to do. Thank you.
Thank you so much. That was excellent. Okay. I think, is Steve going to join me? Oh, we got questions. We have time for a couple quick questions here. Anybody have any questions on what was an amazing talk? Everybody just wants prizes. I'm sorry. We have a question. There we go. I'll repeat it back as well.
So is Gitgo now what you use instead of Git as like a command line utility?
No, so Gitgo is actually meant as more of a drop-in replacement for libgit2, which is, that's a library that if you're writing code that interacts with Git you'd use, it's actually separate from Git itself. The Gitgo does have a command line, it does have a sample command line tool that provides a few different functions, but the idea is more focused around the library components of it.
Okay, we have another question. We have any other questions? We have right over there. Bill, turn around. I like making Bill run around. I'm gonna do this all day.
So what did you do about the inexact reader problem?
The answer is that I spent a long time staring at the output of OD. I can tell you every single command line flag that you can pass to that thing in order to reverse engineer the way that index files work. Index files are a part of Git that are almost completely undocumented. There's like a single ASCII art table in a README somewhere, and that's about it. The compression is based off of a 30-page paper that was written about like 20 years ago. And if you look, there's a mailing list somewhere, post somewhere where the author is like, yeah, I based it off of this paper, but then we stripped out the stuff we didn't need, and then I added some other stuff, so it's really not that anymore. And that's basically what pack files are. So yes, to answer your question, there wasn't really no workaround. We basically just had to find the indices of each object.
Okay, thank you very much.
Thanks.
Okay. Steve, do you want to...